Hello everybody and welcome to chapter number 2. We'll be talking a lot about forces, right-hand methods, vectors, scalars, so many things that are very important for the development of the course. I hope you're reading the book. That's my first advice before getting into this lecture, or just go and repeat the lecture multiple times and then go to the book. That will make sense and that will help you a lot. So when defining vectors and scalars in the book, it talks a lot about that, back and forth, and you have to remember, because this is from physics, that a scalar value is just a number, right? It has a magnitude. It could be positive or negative. When it comes to vectors, they will have magnitude and direction, and we can use different methods to do addition or subtraction or things like that. But from now on, we'll be talking a lot those things, scalars and vectors, and we talk about, or we'll be talking about the addition of those vectors. And this is very important because almost everything that we have in statics will be in vector forces, and we'll need to learn how to do addition and subtraction and multiplication and things like that. So how do you subtract a vector? How do you use the addition for the vector? So for that particular thing, for addition, you have two methods. So one is something that is called parallelogram law. I'm sorry for my accent. And then we have the triangle method. So for the parallelogram law, basically what you do, you will have two vectors, A and B, and you put, tail with tail, and then basically take a parallel vector to B right here, and then do the same thing for A, and then at the intersection you will have a point. Then after that, from the origin, which is 0 right here, up to the point right here, you will have your new vector, and that vector will be the addition of vector A and B, or the resultant vector. If we use the triangle method, it's much simpler. You will basically combine the tip with the tail, and then just as you can see right here, and then the resultant vector will be from the origin of vector A all the way to the end where B is joined with that resultant vector. Or you can do the same thing if you decided to use B instead of A at first. So resolution vector, and that's how they call it, but I always call the resultant vector, but that's fine. Resolution of a vector, basically they have two components for any force. When they're at an angle, you will have a component that it's in the axis direction, and another component that is on the other axis. So right now they call that U and V, but we call ours most of the time X and Y. When we have addition of a system of coplanar forces, right, we'll be using a method to develop them both. So basically what we'll do, we'll resolve the vector using the components, or basically breaking the vector into two components using X and Y axis coordinate system. Each component of the vector is shown as a magnitude, as magnitude and direction. As you can see here, it has magnitude and direction. So the directions are based in the X and Y axis. We use the unit vector I and J to designate for X and Y. I'm pretty sure you already had this in physics, but we're just going through definitions and more definitions. So essentially, if you have the vector F, that F can be broken up into Fxi and Fyj. Okay, because we use the unit vector as they are valued as 1, and they help us establish the direction of that vector. So if you have, let's say, F prime, right, then you will have F prime X I plus minus Fy prime J. What it's trying to show you right here is that they can go into the positive side or the negative side. It doesn't really matter. You will use the signs in order to do that. When it comes to practice the addition of several vectors, the step number 1 is to resolve each forces into components for each one of the vectors, as you can see right here. Then after that, we need to add the x components together, followed by adding all the y components together, and these totals are the x and y components of the resultant vector. Step number 3 will be to find the magnitude and the angle for that vector, and you will be repeating that a lot. So an example of the process right here, as you can see, you have in the first image, you have the different vectors. Then your first step after that will be to decompose those vectors into x and y, as you can see here, and then you have to start doing your calculations of the resultant force is equals to F1 plus F2 plus F3, and then obviously you will start adding or subtracting them all, but always, you know, put all the x together, all the y together, and at the end you will have a resultant force in a vector form that has a y, an I component and j component, or x and y. You know, it's practically the same, they're equivalent. So then after that, if you have your resultant force, you can see it right here. This will be the resultant of the 3 forces that we had. So in order to find its magnitude right here, the way to get the magnitude will be the square root of each one of the components to the square, as you can see here, right? And then in order to get, you know, the angle, is pretty simple, because you are forming an imaginary triangle here which has an angle of theta. So the inverse tangent of those two sides of the triangle, right here and right here, will give you the angle. You can use cosines, you can use sines, and it'll be exactly the same thing. So we have an example, the first one, and this is what I'm doing in these videos. Instead of having different videos with exercises, I'm solving at least 1 or 2 exercises per chapter, or maybe 3 exercises, and you can use that as a base for what's coming. So in this example number 1, you have 3 different forces acting on a tent post. Then you need to find the magnitude and angle of the resultant force. As we practiced before, we need to resolve the forces into x and y components, and then add the corresponding components of this vector, and then after that find the magnitude and the angle of the resultant components. I will usually be solving this by hand, but this is very straightforward, so I don't think it's needed. So you have F1, F2, and F3. So F1 is decomposed in, you know, in I and j direction. So it's 0, obviously, because it's along of the y-axis. And then for F2 right here, you will basically form a triangle. And then with that triangle, and using your cosines, you will get your F2. Then for F3, you will do the same thing, but now, sorry, it is a triangle that goes like this. And then for this one, you will have similar triangle method. This is math, right? You, instead of being given with the angle, you were given with a similar triangle that is also a rectangle, a right triangle, and then after that, use those numbers in order to get the components, and you have F3. What matters for us, right, what is very important, is what do we do when we have all F1, F2, and F3, right? We have, and this is where the analysis will come, we need to find, you know, that resultant force vector. So in order to do that, we have to put all the x components and all of the y components in order to get that vector, and that's what they did. They took F1, F2, and F3 in the I direction, and F1, F2, and F3 on the j direction, and they got the resultant force. Then after that, you just have to find, once you have the vector, it's pretty simple. You have to find the magnitude, right? And I always use these symbols for magnitude, and I'm pretty sure you're familiar with those too, but they don't use that on the book. That's perfectly fine, but the magnitude will be the square root of each one of the components to the square, and then at the end we get this value, and then like we said before, then we have, you know, the angle is equals to the inverse tangent of 2 of the sides. So you have the component right here and the other component right there. You have your angle, and then you get the value. So straightforward, pretty simple. So far so good. If you have questions with the exercise, you can go ahead and reach out to me and I will help you understand that. Okay, so we are going to the second example. So we have a force acting on a pipe, and then we need to resolve the forces into components along U and V axis, and in U and V were given right here, U and V, then we need to find the magnitude of each of these components. So the plan for this will be construct lines parallel to U and V axis, right, and form a parallelogram. Then we have to resolve the forces into U and V components, and then at the end we just have to find the magnitude using the law of sines. So like I said, very simple. We're going to draw the lines as they're given right here, and basically you need to find FB and FU. So as you know, if this is 30 degrees and this one right here, okay, so if you have 30 right here and you have 15 right here, your resultant will be 45. Is that right? Okay, then if you use the 45 and the 30 that you were given, because if it's here then it's here too, then what will be the resultant right here? It'll be 105, right? Well, I hope that makes sense for you. So if you put them together, you should have 180. All right, so then once you do that and you understood, you know, the basics of that, we need to find, you know, the formulas and just do simple math. So the magnitude of those two force components are determined from the law of sines, you know, right here, sine law. Okay, the formulas are given from the figure. Basically, if you have the force and you have the different angles, you can use you know, the sine law when you have A, B, C, and C right here, right here, and right here. So this guy, it's this one, it's this one, and C, it's equals to 30. So that's how you get these number right here, plug into the values, and then get what you need. Okay, very simple and straightforward because everything was given to you from the beginning. If you have a problem with this, like you don't get it, you don't understand it, then reach out to me. Okay, so we have another one. So 3 concurrent forces acting on a bracket. Then we need to find the magnitude of and the angle of the resultant force, and basically sketch that force. So like I said, it's the same thing over and over again. So we have to resolve the forces into X and Y components. We need to add the respective components to get the resultant vector, and then after that it's pretty simple, magnitude and angle. So as you can see here, you have F1. Let's see, so F1, always do this, it's very helpful. You have a triangle that it's like this, and this triangle is equivalent to the 3, 4, 5 that were given. Okay, then using that you can get the components for F1. Then F2, same thing, come right here and draw a triangle. This is very useful for you. So using the sines, because in this case you were given with the 30-degree angle, you can use that triangle and solve for F2. And then finally F3 will be basically the repetition of what we just did. Once you do that, you will get your resultant force by sum all the X and Y's, and at the end you get this. And it's very simple, guys. You just have to get the magnitude of your resultant force, which is given by the square root of each one of those components to the square. You get 546 newtons, and then after that you have to take the inverse tangent of both of the sides in order to get the angle. Okay, it's very simple, it's very easy, and I hope that you don't have any problem with this. So if you have any problem, then come see me and I can help you out to understand this. Okay, And we get to something very important, a very good definition, and it's a unit vector. In order to get Cartesian unit vectors, we need to deploy or use an equation that is giving us the unit of a vector will be equals to the vector divided by its magnitude. Okay, so characteristic of the unit vector, its magnitude is equals to 1. It is dimensionless, sorry, it has no units, and it points in the same direction of the original vector, and that's why it's very important, because we'll do something with this. The unit vectors in the Cartesian axis systems are I, y, and k. They are unit vectors along of the positive x, y, and z axis respectively. Okay, so I goes with x, j goes with y, and then k goes with z. So consider a box with sides ax, ay, and az, as you can see, meters long. Then the vector can be defined as axi, ayj, and azk. The projection of that vector in the xy plane, it's a prime. The magnitude of a prime is found by using the same approach as 2D vectors, which is given by this equation, and then the magnitude of the position of the vector is this, and that's a bunch of blah 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 that you might not get at first. Okay, so what is very important about this is that we understand how these work. When you have 3 vectors, right, in different axes, what you have to do at first is to get the addition of those 2 vectors, and then the resultant of that addition will be combined with the other ones in order to get that. So for example, you have right here your vector A. What I'm trying to say is that you have to go 2 axes at a time. That vector A has a component that is called A prime and also a zk. That A prime has also a component that is called AXI and AXJ. That's the key with this in order to get it. So we know, right, that the magnitude of A, and I always call magnitude like this, it's equals to A prime to the square plus A zk to the square, and that's square root that, right? This is the addition that I'm basically the magnitude that I'm finding for this guy right here. That's the ultimately goal, but we also need to get A prime, and the magnitude of A prime will be equals to the 2 components in the square root. Which ones are the 2 components? So this one right here and this one right there. So you have AXI to the square plus YJ to the square. Okay, and then once you get that, you just basically take this whole thing and plug it right here in order to get, you know, your whole resultant vector. And why is this important? Because with this equation, you know that 1 it's equals to 1 it's equals to A over its magnitude. If you get the magnitude and you have number 1, then you can solve for A and you will get your vector. It's simple as that, and that's what they were trying to show you with this whole blah 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 in this equation, because these guys is what you will find in the book, but it's very important that you know what to do with that. So use the picture and the explanation that I just gave you in order to understand how this works. What is the huge takeaway with this is that you know that vector A will be decomposed per se, or its components will be A prime and A ck, but at the same time A prime it's equals to the 2 components, and you have to put them together into a single equation. And this is very useful, like I said, because you have the value of the unit vector, which is equals to 1, and then if you find you know, the magnitude of the vector, then you can get the vector if that's the case. All right, a little bit more of definition. The direction and orientation of vector A is defined by angles alpha, beta, and gamma. Okay, these angles are measured between the vector and the positive x, y, and z axis respectively. The ranges of values will go from 0 to 180, and right here, by using trigonometry, we need to find, you know, the angles of this, guys. We also need to know that these angles are not independent. They must satisfy the following equation. So cosine of the first angle to the square, square cosine of the other angle, and the other plus the other square cosine of the other angle has to be equals to 1. So how do we picture that? And that's why I have this picture, because this will help you a lot. You know, when you have the vector right here, you have to imagine that you have 3 different planes, and the first plane is this one right here in green. The second plane will be this one right here in red, and the other one will be right here. All of them are right angle triangles, and then based on that you can use cosines and sine in order to find you know, alpha, beta, and gamma. Okay, so for example, this one alpha, it's the angle between it, the z-axis, and the vector A, and beta will be, you know, the angle between y and A. Sorry. Y and A, and then gamma, or alpha, sorry, alpha will be equals to x and A. At the end of the day, and the key with this is that you memorize, or you try to picture that you have 3 different planes right here in a 3D way. Okay, alpha, beta, gamma, it doesn't matter, those will be just angles. Okay, please just keep that in your mind. Those are angles. What you have to know is, by theory, will be the angles of the vector respect to each one of the axes. That's what the theory is telling you, and that's exactly what it is. Okay, these angles are measured between the vector and the positive x, y, and z. That's it. Okay, they call it alpha, beta, and gamma, but it's confusing. At the end of the day, those are angles. Okay, so this result can be derived from the direction of a coordinate direction, angles, and the unit vector. The formula for finding the unit vector, you know, at any position will be, as I said, the vector. You know, this formula right here is the formula with which we started. At the end, it's basically each one of those components divided by the magnitude of the vector. I always use that because that's how I learned calculus when I was learning my engineering courses. So the whole thing with this is that once individual vectors are written in Cartesian form, it is easy to add them or subtract them, and that's the whole thing with this. The process is essentially the same as when 2D vectors are added. The only thing is that you're adding a third component. The thing with this is that you can get easily a resultant force, and that's what you're looking for. So the resultant force will be equals to the sum of all the forces. So you have x directions, y direction, and z directions. And I'm pretty sure you're just getting a lot of flashbacks from physics, and that's exactly what I'm heading. Okay, so for example, if you have vector A and B with each one of the components, then A plus B will be equals to this equation, right? Based on everything that we have talked, and A minus B will be equals to the whole equation A minus B. Okay, subtracting each one of its components. And now we're having an example. So given the two forces F1 and F2, as you can see, we need to find the resultant force in Cartesian vector form. So what do we do? So using geometry and trigonometry, we will write F1 and F2 in Cartesian vector form. Then after that, very simple, add the components together in order to find the resultant force. So if you have, for example, F1, and we'll be just focused on F1 itself, we have that it's equals to 500 pounds, and then we will use similar triangles method in order to find its component on the y-axis and the z-axis, and those components are given right here. There's no F component, Fx component, because it's 0. There's no, the forces are not acting into that direction. So now we will write F1 in the Cartesian form, which is given by this. Okay. Okay, so we know that F2 prime need to be solved into x and y. So at first, we're just going to get the value of F2 prime, and that's given by 800 cosine of 45. Remember, you have a triangle right here. This is the F2 prime, right? But in order to get the F2 prime, you have to take your F and form a triangle. And that triangle has an angle that is equals to 45. So that's why, you know, F2 prime will be equals to 800 cosine of 45. The triangle is formed right here, right? And you're looking for this component. And after that, you have to decompose this particular vector into its component along x and its component along y, and that's why you have F2x and F2y. So if we keep talking even more, what I'm trying to tell you is that the initial vector that we had in here, you know, F2 equals to 800, had components in x, y, and z, and this is a process that you do in order to get them all, and that's what we're doing. So now we're getting F2 as this one right here, 489.9, 282.8, and minus 565.7. So if we add them all together, we have F1 and F2. Basically, and pretty simple, we will just take this one plus this one, and this one plus this one, and this whole number plus this one, and at the end, this is what we get. Okay, and just remember and don't forget the units, because this is a vector force. So now for this one exactly, we need to find basically the magnitude and direction of the resultant force. So right here, what we did, right, we got only the resultant force in a vector form. So how do you get then the magnitude? It's very simple. It's all right here. We have these two formulas that will help us get what we need. Okay. Okay, let's just solve the exercise. So given the screw eye, well, I'm not gonna repeat that, you already saw it, so let's just work it out. Okay, so at first we have F1, and F1 need to be resolved into F prime and F1z, okay, which is this one right here, and then F prime. So if we do that, we do the calculations, because we have the value 250, we have the angle which is 35, and then right here we do the calculations and we get the two components. But F prime can also be resolved into two more components along, like I said, x direction and y direction. And always remember that, because it's the exact same procedure over and over again. So we get F1x, F1y, and then based on that, we will write our vector force, our resultant vector force for F1. So what about F2? So after we do the calculations, like I said, we need to solve F2. We have the cosines because we have the triangles for each one of them. Then we will be solving those triangles by using, like I said, the 400, and at the end we can write F2 equals to this. Okay, so F2 will be equals and given by the cosine of 120 plus the cosine of 45 right here for the y direction, and cosine of 60 for the z direction, and at the end that's how we get F2. So once you do this, right, and you just put x, y's, and z's together in order to put your resultant force as it's showing right here, then using the components is the easiest, because now you just have to follow the formulas that were learned throughout the chapter. The resultant force will be equals to the, you know, each one of the components to the square, all them sum together, and the square root of that will take you to 485 newtons, and then use alpha, beta, and gamma to get, with the formula. So alpha is equals to the cosine of -1 FRX divided by the whole thing, then beta it's equals to FRY divided by the magnitude of the whole resultant, and then gamma will be equals to FRZ divided by the resultant, inverse cosine of all of them, and then you will get your angles, and that's it. So now the position vector, it's defined as a fixed vector that locates a point in a space relative to another point. So let's say we have 2 points, point A and point B, right? And you want to get the vector, the position vector of those. The reason why we're getting this vector is to develop an equation that will help us get forces and things like that. So let's just leave the coordinates of vector A, XA, YA, and ZA, and for vector B, XB, YB, and ZB. What's happening here is that the position vector from A to B, it's denoted as RAB, okay? And it's basically defined as XB minus XA, YB minus XA minus YA, and ZB minus ZA. So what you do at the end is you just have to subtract the tail coordinates from the tip coordinates, right? Because you're going from A to B, okay? So you go from the end to the beginning, and if you perform that subtraction, you will be able to define the position vector called RAB. So why is this important, right? The position vector is important because now we're going to be introduced to another formula in order to find more forces. So you're going to be introduced to something that is called force vector directed along a line. And if a force is directed along a line, then we can represent the force vector in Cartesian coordinates by using a unit vector and the force magnitude. So for that, the first step is to find the position vector. Once you find the position vector, you have also to define between which, point A and point B. You need to define your points. And then after that, you have to find your unit vector as we did it before. So unit vector AB will be equals to the vector AB over its magnitude. And then after that, if you multiply the magnitude by the unit vector, you will be able to find the force vector. And that's exactly what we're looking for, how to find the force that is going throughout that line, specifically for this example. As I always say, there is a lot of terminology, but once we put into the numbers, things will make sense. And that's why I decided to incorporate a bunch of examples in my presentation. So for example, this one, the 420 newtons force along cable AC, which is this one right here. All right, given that, we need to find the force FAC in the Cartesian vector form. So basically what we just did. So for that, we need to find the position vector RAC, and its unit vector UAC. And that will help us to find the force in Cartesian coordinates. Our plan was to find the position vector, and once I had the position vector, I was going to be able to find UAC. How so? Because don't forget that UAC, it's equals to the position vector, right, as a vector over its magnitude. But we also know that the unit vector of AC can be equals to force AC as a vector Cartesian over force AC as a value. This right here is what we need to find. So if we find the unit vector AC, right, the vector, we just did it, and we get the module of that vector, then we will be able to find UAC. And now we put UAC into this equation. I have UAC thanks to this formula, and the module or the magnitude of FAC, it's given right here for 20. So if you plug for 20 and then the resultant of UAC, you will be able to find the vector in the Cartesian mode, and that's the plan. So now that I have RAC that was calculated before, I have that the module is equals to 7 meters. If I use the equation as I was telling you before, we know that UAC it's equals to RAC as a vector over its magnitude, and now I will plug that in here. Since I already have everything, I will just solve for FAC, and now we'll get the vector in the Cartesian form. That's it, and then I get the result. Like I said, don't forget, and let me go back to what I was explaining before. That's what I did. I took basically this whole thing into the equation. I solved for the vector FAC, and I got my force vector, my vector force in Cartesian form. And that's it. Simple as that. If you have any questions, like I said, I'm just putting together lecture and exercises. So shoot me an email. I can repeat that, no problem. Maybe it'll make sense once we get together one-on-one. So, and we're coming close to the end of the chapter, and we're going to study the dot product. The dot product of vectors AB is defined as this formula, and that's given. I'm pretty sure you have heard this before from trigonometry. But basically, the whole purpose of the dot product is to find the angle between two vectors. The angle is the smallest angle between two vectors, and it's always from 0 to 180. The result of the dot product, it's a scalar, okay? Positive or negative number, and the units of the dot product will be the product of the units of AB. If you have forces, you know, it'll be newtons and so on and so forth. For these two vectors in Cartesian form, you know, we will know that we have each one of those vectors will have a component in the x, y, and z direction. So therefore, to find the product will be the multiplication of the x component plus the multiplications of the y components plus the multiplications of the z component. And remember, this is a number, okay? It's a scalar number. Then after that, we need to find the magnitudes AB of the vectors A and B. And using the definition of the dot product, we will have to solve for the angle. Okay, what is the definition of the dot product? Don't forget, let me go back. AB, it's equals to the magnitude times cosine of theta. Okay, so if you want to rewrite that, so dot product of AB, it's equals to the magnitude of AB times cosine of theta. And then if you solve for theta, that's equals to inverse cosine of AB, the product, over AB, the magnitude. Okay, and AB will be equals as the multiplication of each one of the components, and you get the number. Okay, that is simple. So moving along, we're gonna go with an example, as always. So, and I want you to know something. So as we are moving throughout, the class, exercises will get a little bit more hotter, a little hotter. And because of that, I will start doing the exercises myself. I think it's better if you just hear it from me. But anyways, we need to find RAO, the vector force, because let's just read the statement. Read the statement, make a plan, and then execute the plan. So the force acting of the hook at point A, it's given right here. Then they're asking us the angle between the force and the line AO, which is given by the blue line right there, and the magnitude of the projection of the force along AO. So if we want to use what we just learned, we're going to find the position vector AO. So we can use that to find the angle. Why is that? Because we have two vectors. We have the vector force, and we also have the position vector AO. What we're looking for is the angle between them. For that, we will use the dot product. What is the dot product again? A, B, it's equals to its magnitude times cosine of theta. Plug your A, B, and then we have our solution. Okay, so we need to find our AO, and for that we need to define point A right here, which is equals to 1 and I minus 2j plus 2k, right? And 0 or O, it's equals to, the position is 0, 0, 0. Therefore, our AO will be equals to 0 minus 1, it's minus 1i plus 2j minus 2k. And that's my position vector right here. It's defined as perfect. So now if I need to find the magnitude of this vector, and this is meters, don't forget. So if I need to find the magnitude of RAO, will be equals to square root of each one of its components to the square, 2 to the square, negative 2 to the square. If you do the calculations, this is equals to 3 meters. So if now I have that, then I need to remember that my force was giving in Cartesian mode or vector mode, which is equals to minus 6i plus 9j plus 3k. And once you have that, you can get its magnitude the same way you did it before, minus 6 square plus 9 to the square plus 3 to the square. And you get the square root of all that, you will get that that is equals to 11.22 kilonewtons, and that's the magnitude of that particular thing. So if we apply the cross product, right, we know that the cross product F that RAO will be equals to magnitude of F RAO times cosine of theta. If I solve for theta, that's equals to the inverse cosine of F RAO over its magnitude. And all you have to do now is to plug in the values. So now that you have this and you have the formula, you just have to remember exactly what you have and what you don't have. The magnitude, it's very simple because you have already F, which is right here, and you have RAO. If you multiply them together, boom, that's fine. So what about this? How do I get this? For me to get that, remember the definition. It's a scalar. Okay, so I will just multiply the x's, the y's, and the z's of each one of the vectors, you know, my position vector and my force vector, and I will get that value. So if I do that, my F vector times RAO, it's multiplying each one of its components, and that will be minus 6 times minus 1 plus 9, 2 plus 3 times minus 2, and that gives me a value of 18 kilonewtons meters. Okay, so now that I have everything that I need, I will just plug into the equation. So theta, it's equals to the inverse cosine of this value, which is 18, over the magnitude of the vector f, which is 11.22, and the magnitude of the vector RAO, which is 3. When I perform that multiplication and the whole calculation, I should get a value equals to 57.67 degrees. And now that I have my theta, I can get the projection of the force along AO. It's very simple. So the projection of that force along AO will be equals, by using trigonometry, of the force times cosine of the angle between them. I already have 57.7, so I will just perform the multiplication. So that's 11.2 times cosine of 57.67, and I will get a total value of 6 kilonewtons. And that's all. With that, you basically use the dot product in order to get that value. If I'm not mistaken, that will bring us to the end of the chapter. And guys, chapter number 2, and just, wrapping up everything together, is very straightforward. If we think about it, we just learn about forces, how to get the components of the forces when they're in vector form, how to get Cartesian coordinates for vectors giving an angle using the dot product, and so on and so forth. I'm pretty sure this is just an introduction, but remember that you have to read the book in order for this to make sense. Okay, so you cannot rely only on my presentations. You have to do your homework as well, and you also have to read the book, and everything combined will give you the outcomes that we're looking for. So with that, we complete chapter number 2. Make sure you read chapter number 3 before jumping into my presentation. Thank you very much for watching. Email me if you have any questions, but if you don't, I will see you in the next video. Thank you.